I'm Sanjeevan from Shiv Nadar University. For our data structures project, me and my team decided to implement Trie and Skiplist data structure using basic C++ programming. These are my team members, and me and Kesavam VS are going to go through the basic documentation of the previously mentioned data structures. Let's start with Skiplist now.
Skip lists are a modern and efficient probabilistic data structure. They provide faster search, insertion, and delete operation, making them an excellent choice for various applications. Compared to balanced binary search tree, skip list offers similar performance but with a simpler implementation. Skip lists organize sorted linked lists in a hierarchical manner. Each node holds a key value pair and multiple pointers. These are called express lanes, and these enable skipping multiple nodes at once. This setup facilitates quick search, insertion, and delete operation, typically with an average time complexity of overflogging. A script list consists of linked lists organized in different levels, forming an hierarchy. Each node holds integer data and four pointers for moving in each direction. These allow it to skip multiple levels. The number of levels a node is in is determined probabilistically, so higher levels have fewer nodes. In insertion, to add a new node, we traverse the script list from top to bottom to find the right spot. Then, we create a new node with a random number of forward pointers, and then we insert it. Deleting a node involves finding it and removing it from all the lists it's in. We do this by traversing the hierarchy and updating the forward pointers of surrounding nodes. Searching in a skip list takes advantage of its structure. We start at the top list and move down, skipping ahead at each level until we find the target node or reach the bottom. Skip lists are really fast for basic operations like searching, adding, and removing items. On average, these operations are as fast as overflogging, where n is the number of items in the list. But sometimes, in the worst case, it might take as long as overfill because of how the skip list works. Advantages. Skip lists are easier to understand and maintain compared to balanced binary search trees. They offer overflog and average time complexity for search, insertion, and deletion. They can handle concurrent operation, making them suitable for parallel processing. Disadvantages. The random determination of levels and forward pointers can sometimes lead to suboptimal performance in certain situations. They require more memory to store multiple levels of lists and forward pointers. This can be higher compared to simpler data structure. If the distribution of the node height is imbalanced, the skip list can become skewed, resulting in decreased performance for certain operations. While skip lists can be parallelized, coordinated concurrent operation can be more complex compared to other data structure application. Skip lists are used in database indexing to efficiently search, insert, and delete data. They are employed in web search engines for fast lookups of web pages and other content. They are used in network routing tables for efficient routing and forwarding of data packets. They are used in multimedia streaming services to manage and retrieve multimedia files. They are utilized in caching systems to quickly retrieve cached data. They are also used in distributed systems to maintain dynamic and balanced data structure. Conclusion. Skip list offers fast search, insertion, and deletion. Its hierarchical structure enables quick navigation. They take some memory for performance benefit. They are ideal for various applications due to their efficiency and simplicity.
Now let's have a look at the Trie data structure. The TRIE of Trie stands for the tree in retrieval, but is pronounced Trie to avoid confusion with its namesake. Thus, the computation function a trie excels in is retrieval or search. This is done by efficiently storing and retrieving strings by organizing them in a tree-like structure as shown in the slide. A trie is composed of multiple nodes branching out from a single starting point, which we'll be calling the root. Each node contains an array of node pointers to point to the next node and a boolean value to mark the end of a word. The number pointers in the array, in this case, has been set to 128 to accommodate every single ASCII value. And we'll have a pointer pointing to the root node of the tree. Let's move on to methods of a tree. When inserting a new key into a trie, we traverse the trie from the root, accessing the nodes corresponding to the characters of the key. If a characters node doesn't exist, we create it, and once we reach the end of the key, we mark the node as a final node to indicate the completion of the key. Searching in a trie is incredibly efficient. We start at the root of a trie and traverse through the trie, accessing the nodes corresponding to the characters of the key to be searched. If we encounter a null pointer before reaching the end of the key does not exist in the trie. Otherwise, if we reach the end and the node is marked as a final node, the key exists. To delete a key from a trie, we first perform a search to find the key in the trie. If the key exists, we mark the node representing the end of the key as a non-final node by changing the boolean value. Then, if the node has no other children and is not marked as a leaf node, we recursively remove the node and backtrack until we reach a node where any of the above condition is satisfied or the root node is reached. As you can see, the trie has a really optimal time complexity for common operations. An insertion of O of n, a search of O of n, and a deletion of O of n. In all these above cases, the n represents the length of the key. The high efficiency shown in tries makes it a really good data structure in dictionaries and spelling applications which require quick retrieval of strings. Searching words with a common prefix is also easier, as you just have to traverse down the trie from the node with the end of the prefix. Trie also helps in optimizing space usage, as in case of words with common prefixes, each letter need only be stored once. On the other hand, it also has some downsides as well. One of them is the memory usage in cases where words rarely have the same prefixes. In these cases, the need for pointers to refer to child nodes proves to be harder on the memory. In such cases, other data structures like hash tables or binary search trees prove to be a better solution. And so, the real-world applications of tries include cases where the searching of a string plays a really important role in the function. Some examples are IP routing. To efficiently match IP addresses to the corresponding destinations, tries are a really efficient implementation. And also in cases of autocomplete and predictive tests, to efficiently predict and suggest words based on partial inputs, tries are implemented. They are also implemented in spell checkers to enable fast and accurate spell checking by quickly verifying the existence of words in a dictionary. To summarize, tries are a probabilistic data structure that offers efficient search, insertion, and delete operations. Retrieval of strings is the best implementation of a trie. Being a relatively complex data structure, it trades memory overheat for enhanced performance. Thank you for your time.